The Adaptive Levels of Autonomy for Unmanned Air Vehicle Supervisory Control is an SBIR effort conducted by OR Concepts Applied for AFRL HECI. In this effort, ORCA devised an architecture suitable for a multiple UAV control station emulator that allows testing and evaluating different methods for adaptive levels of autonomy. The following is a demo of the prototype product for this effort, which will serve as a research testbed for studies of the roles of humans and autonomy in controlling multiple UAVs. The ALOA prototype is built with Opus 3 components. ALOA-specific components are plugins to Opus. Opus provides tools for mission planning, analysis, and simulation. The software is flexible enough to provide interfaces for an operator and an experimenter. Components have been tailored for each.
In this scenario, I'm commanding 4 UCAVs equipped with a variety of sensor and weapon payloads. We've been tasked to fly across Iran doing Rec-E. We've been authorized to take out 4 high-value targets, if they're still there. The fans emanating from the threats represent threat exposure, showing when and how long the vehicle's exposed to the threats. Similarly, the fans from the route to the target represent objective fans, showing when and how long an imaging or weapon release task is accomplished.
In the Experiment Control tab, the autonomy levels of the sortie's auto-routing, weapon release, and imaging can be set. There are several levels of autonomy included for auto-routing in the software. Similarly, there are several imaging autonomy levels. The script editor lets me script events for repeatable experiments. It is essential in setting up my experimental controls. The timeline header at the top indicates the control simulation time and simulation interval. The timeline event below contains icons representing events. Events include adding and deleting threats, executing a test, and setting the autonomy level. It's important to measure how the operator is reacting and responding to the experiment. 2 tests that can be performed are the Red Plane Test and the Situation Awareness Global Assessment Technique, SAGAT. In this test, we place a red plane on the screen and measure the time it takes for the operator to see it and enter some random text. In the SAGAT test, we blank the operator's screen and ask questions to assess his situational awareness. Now I will set the autonomy levels for the different sorties.
On the overview page, I get a graphical summary of the quality of each sortie's route and an indication of when objectives will occur. Each rectangle represents a period of time along the route. The colors provide insight into the danger level at a particular time. Black means a likely SAM shot. Even though no one's in the plane, it'd be nice to get them all back. I can view weapons footprints and sensor footprints. These threat templates will show when a vehicle can be detected by a threat system. Okay, more images to identify. Uh-oh, more pop-up threats.
Based on the auto-router autonomy levels I said earlier, the operator will be required to do more or less work for each sortie during this replan. I can run the experiment again and adjust the autonomy levels to collect more data.
I can compare the effectiveness of the route I manually edited to the one the auto-router generated.
The first red plane test was easy and the operator performed well. This part of the experiment will be more difficult for the operator. Now we'll see how long it takes for the operator to notice the red plane. One reason for doing these experiments is to find out the nature of the relationship between the types and amount of operator activity to his reaction time. Typically, there is a bathtub-shaped curve that describes this relationship. That is, too little or too much activity results in slow reactions. Determining the curve's exact nature in this domain requires further study.
The prototype Aloha software is a research testbed for studies of the roles of humans and autonomy in controlling multiple UAVs.